Thank you, Gary. Gary, thank you for the introduction. I don't use everything. I don't use EM yet, but probably after this meeting, I will. So let me start by thanking the organizer. It's a real pleasure to talk at this meeting. It's actually my first one, so I hope in the future I can attend in person and not virtually. All right. Already having issues? No. So I want to touch on two topics today, if I have time. First, I will go in detail into neutron crystallography and how we use this technique to, in complementarity with X-ray crystallography, to look into enzyme chemistry. And the enzyme I'm interested in is Iytic polysaccharide monooxygenases, which are a metalloenzyme. And an added advantage here of neutron is to be able to look at the metalloenzyme in its native state, so without inducing radiation damage during the experiment. If I have time, I will also show you how we can use neutron small angle scattering to look at complexes. And here we're interested in looking at the complex of LPMO with its redox complex, which is redox partner, sorry. And before I start my talk, because life is what it is right now, I just want to give you the take-home message. Really, the take-home message of this talk is that neutrons are sensitive to hydrogen and its isotope deuterium. So we can visualize the position of hydrogen atom in enzyme, providing experimental insight into enzyme chemistry. Again, this method is not used alone, it's used in complementarity with X-ray crystallography and GFT calculation, for example. Another important take-home is that neutrons do not induce radiation damage. Therefore, we can look at middle center redox cofactor without perturbing their redox state. And finally, with small angle scattering, we can map complexes in solution. So I do not have to tell this audience that X-ray crystallography is today the method of choice in order to determine protein structure. And while EM may very soon be the method of choice to also reveal the position of hydrogen atom, as of today, neutron protein crystallography really has a unique role in being able to reveal protonation state of amino acid, an ambiguous orientation of side chain or water molecule that play an important role in enzymatic mechanism, and together for certain residues such as histidine or tyrosine, both the protonation state, but also the orientation of those side chain. Orientation of histidine can be difficult to determine from X-ray data alone because carbon and nitrogen scatter similar ways, but here if we can see deuterium, we can now more easily orient the side chain. And in the case of hydroxyl group, it can be difficult to determine hydrogen bond interaction, but again, if we can visualize those hydrogen and deuterium position, it becomes unambiguous. So again, we always start with X-ray, an X-ray structure, and if that X-ray structure doesn't answer the question that we have about enzyme chemistry, we then move to neutron crystallography. So why, and Ketoro actually already answered that question, why do neutrons see deuterium? And I will come back in a second why I say here deuterium and not hydrogen. So as Ketoro indicated, X-ray interact with electron clouds, and the magnitude of the scattering is proportional to the the number of electrons in the atom. So hydrogen and deuterium with only one electron are hardly visible in X-ray maps. However, neutrons interact with the nucleus, and the magnitude of the scattering depend on the complex structure of the nucleus, and there is no correlation between the size of a nucleus and its interaction with neutrons. So what this schematic represents here is that hydrogen and deuterium have similar magnitude than other atoms found in proteins such as carbon, oxygen, and sulfur. What this scheme also illustrates is that neutrons differentiate between hydrogen and deuterium, that deuterium is a stronger scatterer than hydrogen, but also that deuterium scatter neutron with the same sign than carbon, oxygen, and sulfur. So this is the reason why we prefer to use deuterium labeled sample in neutron crystallography. We simply see deuterium better than we see hydrogen at the typical resolution that we can get, which is between 1.8 angstrom for the best neutron structure and 2.5 angstrom. So you can see here on this phenylalanine residue that you can model very well at 1.7 angstrom room temperature the deuterium on the cycle and also in this hydroxyl group, because this protein was per-deuterated. But if the protein is not per-deuterated, then we don't really have information on the hydrogen on the cycle, but we do have a good data for the hydroxyl group. So this is really the main difference between neutron and X-ray crystallography. When you do the experiments are the same. You start from a crystal, and of course, whenever we mention neutron crystallography, we immediately think about large crystal. And the reason is that the neutron sources that are available anywhere in the world are many orders of magnitude weaker than the synchrotron available, or even your X-ray source at the basement of your university. So we need to start with large crystal. We collect diffraction data. We often collect in the Larwo mode to increase the flux on our sample. But then things are fairly easier because we already have an X-ray model when we start our experiments. So we already have a set of phase. We don't need to we need to phase, but we have a starting model, sorry. And then refinement software like Phoenix Refine have been very well developed to handle those refinement against neutron. And the model that we obtain, again, include all the atoms. So we have the position of hydrogen and deuterium atom. And if we are looking at metalloenzyme, then we look at metal center that are unperturbed. So briefly to introduce the protein that I'm interested in, my group is interested in, Iytic polysaccharide monooxygenases. Those enzymes have been discovered in the early 2010s. They are enzymes that are involved in cellulose degradation in wood-degrading organisms such as fungi. So those enzymes are copper monooxygenases. Their active site is composed of one copper atom located on the cellulose binding surface of the enzyme. The enzyme requires the input of molecular deoxygen and electron in order to break the cellulose chain. And when those enzymes were discovered, it was found that they boost the activity of the classical glycoside hydrolase by creating a new end chain that those GH enzyme can then access. So they have an important industrial role in the degradation and the efficient usage of biomass. So as I said, those enzymes have been fairly recently discovered, and there is a lot of questions that remain about their enzymatic mechanism. Really, only the first couple of steps are known, are well known, and do not have question about them. So in the resting state, the copper is found in the redox state 2, and upon reduction by 1 electron, copper 1 has high affinity for molecular deoxygen. The copper is reoxidized, forming this superoxide species. So this first couple of steps are unquestioned, but what happened next is really the question. Which species is the hydrogen atom abstracting species on the substrate? Is it the superoxide species, or are there additional proton and electron transfer that lead to oxyl copper intermediate that is then the hydrogen atom abstracting species? So this question is open, And this is the question that we're trying to address using neutron crystallography, because you can see that in order to determine which route this enzymatic mechanism followed, we need to see hydrogen and find out where they're coming from. And here, just to orient you in the next slide that we will look at, this is the active site of the enzyme with a copper atom, which is coordinated by a so-called histidine brace, composed of the first histidine in the protein and a second conserved histidine, in our case, histidine 84. So as I mentioned before, we can't talk about neutron crystallography without talking about growing large crystal. And again, this is because of the low flux of neutron available. And very often I will hear, oh, neutron crystallography, you need very large crystal, it's difficult. What you really need is well-ordered crystal that diffract X-ray to high resolution. So in this case, here we have those plates which are not large volume, not very good looking crystal, but this plate diffract X-ray to 1.2 angstrom resolution, meaning that the order is there. So if you have crystal like this that diffract to high resolution with a little bit of effort, of course, at the bench, using technique like seeding, micro-seeding and macro-seeding, I'm confident that you will be able to grow neutron that are large, crystal that are large enough for neutron diffraction. So well-ordered crystal is really key. And then when you have those crystal, as I mentioned earlier, we really see deuterium better than we do see hydrogen in our structure, so we exchange. There is a second reason why we exchange, is that if you look at the schematic here, the red and green is illustrating what I said about scattering with a positive or negative lens earlier. And now this black and gray signal incurrent scattering from hydrogen and deuterium. And you can see that hydrogen has a very high incurrent scattering. That means very high background. So we want to get rid of that. So by exchanging the solvent in our crystal to deuterium, we reduce the background a lot, and we exchange hydrogen for deuterium in the protein. So at the Crystallography lab, we have two facilities. We have a diffractometer at the steady state source, which is an instrument that, if you are in Europe, is similar to the LADI instrument at the ILL or the BioDiff instrument in Germany. And at the spallation source, we have an instrument that would be similar to the JPARC instrument in Japan, if you are in Asia. So those two instruments have very similar performance. They differ a little bit in the size of the unit cell age that they can cope with. So let me tell you a little bit about how we use neutron crystallography to look at the structure and try to elucidate the enzymatic mechanism of LPMO. So we first again start with X-ray work. So we first solve an X-ray structure of the enzyme in the resting state, so with the copper in the redox state 2. So we solve that structure at 1.2 angstrom resolution, and we observe the active site copper coordinated to the histidine brace and to two water molecules in the equatorial and axial position. And we also observe in that structure a molecule of the oxygen, which is bind a little bit remote from the active site. So we have our starting X-ray structure. We then solve a neutron structure at room temperature. Again, we have no radiation damage using neutron diffraction, so we can do those experiments at room temperature and solve a structure at 2.1 angstrom resolution. And I'm gonna try to play that little movie just to show you how that density looks. So we can see the histidine that coordinate the copper and determine their protonation easily. Not that this protonation were in question. We can see the protonation state of the N-terminus, and I'll come back to that later, which is an NH2 neutral group that coordinate the copper. We can see hydrogen bonding between this tyrosine, which is kind of a distant ligand of the copper, with this glutamine. So this crystal were hydrogenated protein exchanged to these two. So you can see that the density is fairly clear for the deuterium atom, but wherever we have hydrogen, like here we have a CH2 group, we have this cancellation that I mentioned. So again, we see deuterium much better than we see hydrogen at the typical resolution that we can achieve for protein crystallography. So there were not really any question about the protonation state at the active site in the resting state. But what was interesting in that structure was to be able to both orient and determine the protonation state of this second shell histidine 157 here, which is a conserved histidine among in this class of LPMO enzyme. And as I mentioned earlier, with X-ray data alone, it can be difficult to orient an histidine because carbon and nitrogen scatter in the same way, and you have no hydrogen to help you differentiate between this conformation and the flip conformation. But here with neutron scattering, we were able to unambiguously determine that this histidine was singly protonated at the N epsilon position. And to convince the reviewer, we calculated every possibilities. So in one orientation or the other, and either singly protonated or doubly protonated or singly protonated at the N delta position. And you can see that unless we are in this conformation with the N epsilon protonated, we have a warning sign in our FO minus FC neutron SNG maps, where we have negative peak that appear when or positive peak that appear when the protonation state or the orientation is not correct. So this was our first neutron structure, which was published a few years back. And then the follow-up step, again, remember we're trying to elucidate this pathway and find which ways the reaction evolve. So our next step was to create this reduced copper 1 intermediate state. So again, we started with X-ray. We used similar crystal that we treated with ascorbate in order to reduce the copper. And what we observe in our X-ray density map, electron density map, sorry, is that now we have displaced the equatorial water molecule, and we can now model the oxygen species here in the equatorial position. We model this species as a peroxo species. However, because we do not have position of hydrogen, we cannot really discriminate between peroxo and superoxo. I also want to mention that we may have had a little bit of radiation damage in this structure. The occupancy of this the oxygen species is around 0.6, and this actual water molecule, which should be displaced, is around 0.4. So we probably have a mixture of state of thing going on here. So we followed up this work with a neutron structure. Again, we use large crystal that we treat with ascorbate. And in this case, in order to trap this intermediate and reduce thermal disorder, we collected a structure at 100K. And now we are able to model this deoxygen species as a peroxo species. And now we have an occupancy for that superoxo species of 1. So the question then is, where does that proton come from? So in the literature, there's been proposal that based on small molecule mimic, that the N-terminus of the enzyme could be the proton donor. So we calculated some omit map, omitting either one deuterium or the other of the NH2 group of the first histidine. And this histidine is unambiguously, sorry, this NH2 group is unambiguously protonated at both positions. So the proton is not coming from the NH2. Now, we look at this second shell residue, histidine 157, and to our surprise, this histidine appeared to be doubly protonated at both the N epsilon and N delta position. So the data suggests that this histidine 157, under the condition of our experiment, which are an absence of substrate and in absence of substrate and on the crystallographic parameter that we have, is the proton donor to this species. So this is a little bit unexpected to have a deprotonated histidine. So we are complementing this data now with DFT calculation, but we've also looked, tried to probe a little bit further this histidine 157. So we do our experiment around a pH around 6.5. Those enzymes are most active around pH 5, at which pH we could expect this histidine to be doubly protonated. So we did a low pH structure, both with Neutron and with X-ray, and we find that even at low pH, pH 4.8, that histidine, again, surprisingly, remain singly protonated at the N epsilon position. So we did that Neutron structure, and then in order to change the buffer, change the pH, we use vapor exchange. So in order to really confirm that protonation state was correct, we also did an X-ray structure where we soaked the crystal, small crystals soaked at pH 4.8 to really fully change that, drive that pH down. And what we observe is that this histidine actually doesn't move. It's really locked in place and it cannot accept the second proton because there's some steric clashes here. So what we now think is that because of our crystal packing, this histidine 157 is locked in place and cannot go out, whether it's at low pH or when it is in presence of the oxygen species coordinated to the copper. It cannot flip out to the bulk and grab that proton and come back in and transfer that proton. But there are evidence in the literature and in structures solved by other groups that this might be what this histidine is doing. There is indeed a number of structures where that histidine is refined in an outward position. So in summary, we're using X-ray neutron crystallography to provide complementary insights in the LPMO mechanism. And we start with X-ray structure, and if the X-ray structure doesn't answer the question we have about the chemistry, then we turn to neutron. And in the case of LPMO, we could determine the chemical nature of the dioxin species coordinated to the copper after ascorbate reduction, and we can identify the proton donor to that deoxygen species. Of course, we are further digging into the role of this histidine and other residues. So I'm going to take a break and just thank the people that have been involved in this work. So Brad Odell has done the preliminary work on the LPMO mechanism, and Gabriela Schroeder, different project, has been doing the ascorbate soak. And I think I'm running out of time. If not, I can tell you a little bit about small angular scattering. That maybe. I
think there are 5 more minutes, but I wanted to have it for questions.
All right.
Yeah. If you have to say something for 1 more minute, you could.
Oh, all right. Okay, so I'll go very fast. I just want to mention, so we've looked at LPMO using crystallography, high resolution structure. What we're also interested to probe is its redox partner and how electrons are transferred to LPMO. This redox partner is a 2-domain protein with a long flexible linker, difficult to study by X-ray crystallography. So we are using small angle scattering. As you know, it gives you molecular envelope, not atomic resolution, but it's very efficient to look at conformational reorganization in multi-domain protein. So the advantage of neutron small angle scattering over SACs is that we can use hydrogen deuterium labeling in order to highlight different components. So if you look at X-ray and you look at your LPMO redox complex, you may see a blob. But if you use neutron with deuterium labeling of LPMO, then you can only see your redox partner and you can probe the structural rearrangement of this redox partner. So we did an experiment where we've labeled LPMO so that we would not see, so LPMO is invisible in our experiment, and we only look at the redox partner and how its conformation is rearranged upon binding to LPMO. What we see is that when we increase LPMO, we decrease the radius of, the maximum dimension of the redox partner and its radius of gyration, suggesting that LPMO receive electron from a more compact form of, the redox partner. And this is just a small diagram, again, to illustrate that in presence of LPMO, the redox partner adopt a close conformation. Right, and
thank you. It was very nice.